among hundreds of MIT courses. Visit MIT OpenCourseWare at ocw.mit.edu.
All right, welcome back to 6890. Today we continue our theme of reductions, NP hardness reductions from 3 partition. Yesterday we saw a couple of different reductions from 3 partition and then a bunch of reductions from those problems, various puzzles. The last one we covered was packing squares into a square. This is just a reminder visually what it looks like. But we're going to just take this result as given, and our first NP hardness reduction will be from packing squares into a square. And then we will see a bunch of, possibly as many as 8 reductions from 3 partition. So, without further ado, let's get started. The first problem we're going to talk about is edge unfolding polyhedra. This is a geometric folding problem. So if you're interested in more, you can take 6849. But here's a simple, if you've ever made a cube out of paper, probably you cut out a cross shape and then folded it into the cube. But if you want to know what shape should I cut out to make a cube, then you want to know where should I cut, which edges of the cube should I cut. They're drawn in red here, so that when I unfold it, I get one connected piece without overlap. So for surfaces that are topologically a sphere, you want to cut along a spanning tree of the edges. And for a cube, that will always work. But for some polyhedra, like these two, when you unfold, you get overlap. And in fact, no matter which spanning tree of the edges you take for either of these 2 polyhedra, you are guaranteed to fail. You cannot make these out of one piece of paper by folding and get an exact cover. So that's bad news, and these are old results. These are back in 1998. But it remained an open problem. How many other examples are there? If I give you a polyhedron, I want to know, is there an edge unfolding? We only cut along the edges. What's the complexity of that? And the answer is, it's NP-complete. Strongly NP-complete, slightly stronger. This is not obviously a number problem, but in geometry you have this issue of what are the coordinates of the vertices. So the coordinates could be exponentially large, or they could just be polynomially large. Here they only need to be polynomially large, so strongly NP-complete. This is a complicated proof, so I'm just going to sketch the idea of how it works. At the beginning, like most proofs, there's some kind of overall infrastructure that holds all the pieces together. This is one part of that. Well, this is the main infrastructure in this reduction. There's some stuff around the side that's mainly to make the surface topologically a sphere. The focus is on a square face here it has a little slit in it, and there's a tower coming out. It's drawn edge on here. This is the part we actually care about. I think actually it'll be redrawn here. So we'll really just be thinking about this, and then there's some stuff that wraps it around and makes it a sphere without changing unfoldings. So don't worry too much about that. Mainly, lecture 3. Alright, welcome back to 6890. Today we continue our theme of reductions, NP hardness reductions from 3 partition. Yesterday we saw a couple of different reductions from 3 partition and then a bunch of reductions from those problems, various puzzles. The last one we covered was packing squares into a square. This is just a reminder visually what it looks like. But we're going to just take this result as given, and our first NP hardness reduction will be from packing squares into a square, and then we will see a bunch of, possibly as many as 8 reductions from 3 part into a plus sign. Most of it is lots of tiny stuff called atoms, which we will get to. And then the interesting part from a 3 partition standpoint, from a square packing standpoint, is there are some square faces. And because we're edge cutting our surface, those squares will remain squares. There's no edges on them. So those guys somehow have to move around when you unfold, and it's not drawn this way, but the squares are large enough that they can't fit up the chimney. Okay, this chimney is actually pretty narrow, constant width, and those guys are all really big. So this other stuff can move up the chimney. The squares will have to stay in this square, and that's how we're going to get packing squares into squares. Okay? Now, the challenge is, what we want to be able to do is move the squares around freely. But in reality, we need to make a connected 2D shape. So somehow we need to connect together these squares by some stuff, that's mystery atoms, so that basically for any square packing we can arrange to have those faces in that rough arrangement, and then the other stuff somehow connects everything together, and whatever doesn't fit in here goes up the chimney. So that's the plan. If we zoom in, right, so this is sort of the diagram of that plan. Imagine you have some placement of the squares, and we're going to try to connect all the pieces together, maybe to some common root in the lower left corner. First, we're just going to draw some L's conceptually to connect them all to here. Those cross, which is not allowed. But then we're going to reroute the L's to go around the, so to get up to this box, we're going to go around all of the other boxes below it. And in this way, we get a non-crossing arrangement. If we zoom in even closer, these are drawn as lines, but really they're little strips of paper. And they may do weird things like zigzag back and forth. How that happens, we'll see in a moment. But this is to convince you that at least if we could place squares, and they're not like right touching each other, so we're going to shrink each square a tiny bit. I won't get into the details, but if they're integer squares, let's say, then we'll shrink them maybe by -1/n or something polynomially small. And then that gives us a little bit of room to route all of these paths and make them like 1/n squared or 1/n cubed in thickness. Still polynomial, so still strongly NP-hard. If we have a square packing, we can connect them all up in this way if we have these magical atoms that can do whatever we want freely. And that's the, so in a little more detail, in this picture, we imagine the atoms as somehow being connected together in a chain, potentially, and then when they unfold, this is the fun part. So we maybe, for connectivity purposes, maybe first we want to visit B1, then we want to visit B2, and so on. And that corresponds to some traversal on the surface of this plus sign, or the tower that's sticking out. And then in 2D, when we unfold it, we have a different thing in mind of whether we want it to go left or right. So there's moving left or right intrinsically on the surface, and then there's moving left and right in the unfolding. So two separate things, and conveniently, this one structure, is one of these boxes, this is what we call the atom, can do all of those things. Certainly not obvious from the picture, it's just a little bumpy square, but you just trial the cases. These are 3 of the cases, not obvious, but they turn out to be 10 after you remove reflections and rotations. There's a few things going on, but the main thing going on is whether you're going left or right in the, get this straight, whether you're going left or right intrinsically on the surface, and whether you're going left or right or straight in the unfolding. So here you can see you're turning left in the unfolding, you're going straight in the unfolding, and you're turning left in the unfolding. So the second coordinate is L, S, L. What's less obvious is if you fold this up and you get the atom structure, but the thing that you attach to here is on the folded structure either to the left or to the left or to the right. So you just check all these things, and then this is like a universal glue that can connect together the squares however you want, both on the surface, where they have to be connected originally, and in the unfolding, where you want to match some square packing. So we'll have a little bit of hand waving there, lots of hand waving, but in the end you get strong NP completeness of edge unfolding polyhedra. Any questions? All right, perfectly clear then. Let's move to another puzzle. This is called the snake cube puzzle, or the Kubra puzzle. Here is one instantiation of it. So we have, it's a chain of blocks try to unfold in a way that I can put it back together, because it's actually quite tricky to solve. It's a chain of blocks, and there's an elastic through the centers, going through the center of the faces. So the result is you can't really pull the squares apart. It's a pretty tight elastic, but you can spin, because from the elastic's point of view, these are all equally happy. So you're basically told that, I could also spin here, but it doesn't do anything. I stop at a 90-degree angle. So I'll force the constraint here.